Okay, so we ended here in the last lecture, that is the space-time the propagation of an electromagnetic wave. And in the space-time propagation we discussed about the direction of the electric field vector, direction of the B vector, and the Poynting vector, which gave us the flow of radiant energy as well as the propagation of the wave. Now, it is very important to understand that we are discussing here about radiant energy. We are not discussing about the total energy. When we talk about, if you're talking about this thing here, the Poynting vector, then we are talking about radiant energy. And what does radiant energy means? Radiant energy means the energy radiated through this electromagnetic field. Every field has its own energy. For understanding the concept, we need to understand that the energy density that an electric field has, it also has a formula, and that energy density, if I denoted by E, I'm using D for density and small e for electric field, will be equal to half epsilon naught E square. Okay, and similarly, if we consider the electron density for, let's say, B, or let's say it is M for magnetic field, then it will be B square by 2 mu naught. Epsilon naught is the permeability and mu naught is called the permittivity, which I by mistake wrote in the last lecture. So this is the permittivity. Okay. So this also has energy. So this is the energy that we're talking about. This is the average energy that we're talking about, and this is the radiant energy, but not the total energy. Okay. So this is the total density of the energy that is traveling. And this all waves are characterized by three things. The three things that we have called the characteristics of the wave are the frequency, the wavelength, and the speed. Okay, so these are the three things. The first thing is frequency, right? The second thing is called the wavelength, as it is the name suggests, the length of the wave. And the third thing is called the speed of the wave, or I will just write speed. Now, the frequency is defined as the number of waves or cycle. If we have like this, then the number of waves, okay, let me draw it a little bigger. Okay, so it is like number of waves per second that pass through a given point in space. Like I suppose I assume this point here like this, then the number of waves that pass through this point in a second is called the frequency, right? And it is denoted by the symbol mu. Okay, the symbol nu. Okay, and then comes the wavelength. To discuss about the wavelength, let's draw a wave like this. Let's say this is a wave, and we draw two peak points here, the two peak points. Then the distance between these two peak points is called the wavelength. The distance between two consecutive peaks or trough in a wave symbolizes the wavelength. So what is a trough? The trough is this. This is the trough, and this here is the peak. Okay, this is the trough and this is the peak, right? So the distance between these two peaks is called the wavelength, right? Now there is a relationship between this wavelength and frequency, and it is given by lambda into mu is equal to c, and we know the c is the speed of the wave. So we know that a wave is moving in this direction. If I draw a wave like this, right, This wave is moving in a direction and let the speed be c, and this c speed gives a wavelength lambda and a frequency of mu, then lambda into mu is equal to c. Right. Now, using various experiments and mathematical calculation of these two things here, using these two things, it has been proved that the speed of an electromagnetic radiation, an EM wave is constant. It is constant. Right, it is constant, and this constant is also the speed of light, because light itself is an electromagnetic radiation. Therefore, this c is equal to 3 into 10 to the power 8 meter per second. Okay, so lambda into mu is a constant, right? But unlike speed of light and wavelength, which change as electromagnetic energy is propagated through media of different densities, frequency remains constant and is therefore a more fundamental property. We know that if in case we have a slab like this, let's say we have a slab, this is a glass slab, so this is made of glass, and light falls on this like this, then it comes out at a different angle. This is because the speed of the light changes in that medium. So this is called refraction, and we see that the wavelength and the speed changes, but the frequency does not change. Therefore, it is a much fundamental property. Also, you can see that if this is a constant, then lambda in mu is a constant, and therefore if lambda increases somewhere in that region, mu has to decrease, and if lambda decreases somewhere in that region, mu has to increase. Okay, so a high frequency wave has a lower wavelength and a low frequency wave has a higher wavelength. Right. Now there is also a definition called the wave number, which is defined as the count of the number of wave crests or troughs in a given unit of length. So if I have a length like this, let's say I complete this wave like this, and I take a unit length of say 1 centimeter, and I count the number of troughs in there, then that gives me the wave number denoted by nu bar. Okay, and it is given by the formula mu upon c, the frequency upon the speed, and which is 1 upon lambda. So 1 upon lambda is equal to the wave number. We see that in atomic structure it is more important, or it is more feasible to discuss about wave number than a wavelength. Okay, so this is the characteristic of wave, of our electromagnetic wave. Now let's discuss a very little about a particular nature, and in the later lecture I will discuss about the two experiments that led to the discovery or the point that there is also particular nature of radiation. Okay, so radiation can also be described in terms of particles of energy. They can be also described by particles of energy, and we know by our normal day-to-day life that these particles of energy are called photons. These particles of energy are called photons, and the energy of these particles, the energy of these photons, is given by a quantum formula called the Planck's formula, and is given by h into the frequency of that photon. So h here is the Planck's constant and has a value of 6.626 into 10 raised to the power minus of 34 joule second. Okay, and this is the energy of a single photon, And this all can also be written in the form of hc by lambda, so that we can also find the energy of a photon using the wavelength of that particle. Okay, now we see that these two things here, the mu and the lambda, tell us the relationship with the wave characteristics. So somehow the particulate nature is related to the wave characteristic of our electromagnetic wave. Also, a second point that about photon is, even if this is a photon that we have like this photon has neither mass nor any charge. It is very difficult for us to understand that how can something exist but has no mass. But we need to understand that it has some energy, and it follows the Einstein's famous equation of mc square, which is equal to energy. Therefore, we can say that if has some energy, then it has some effective mass, not mass, but effective mass of E over c square. And it is a very large concept of why there is no mass, but about using the Einstein theory of relativity and this equation, and which will be dealt in some other type of lecture. So we just needed to mostly know about the particulate nature of radiation, or the quantized nature of radiation. Like the energy that we have, let's say we have this energy, then we can divide this energy into various packets, and one of these packets can be termed, let's say this packet can be termed as an individual photon or a packet of energy. So we have quantized the energy rather than being a continuous source of energy.